This is a screencast on a related rate problem. This example concerns ascending in a hot air balloon. Let me read you the question. A hot air balloon is rising straight up from a level field, and its ascent is tracked by a rangefinder 150 meters from the liftoff point. At the moment that the rangefinder's angle of elevation is pi/4 radians, the rangefinder's angle of elevation is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Two things that I like to do when I start a word problem like this is, one, draw a picture of what's happening, and two, determine some variables that are in the problem that I'm going to use. Having variables is an important part of translating a verbal description of this scenario and the functions here into symbolic form. Once they're in symbolic form, I can apply the analytical tools of calculus to come up with an answer. So first the picture. We have the level ground. At one point on the level ground we have the balloon ascending. And I'll draw a cute little balloon here. At another point, 150 meters away, we have a rangefinder. And think of that as a telescope. And the telescope points at the balloon. And the angle the telescope makes with the ground, right here, that's what we call the angle of elevation. So let's say theta is the angle of elevation. And according to the problem, the angle of elevation is measured in radians. We want to know about how fast the balloon is rising at the moment. That's a question about its upward speed, so I want to define a position function. I'm going to say h here is the position function. H is the height of the balloon. And because our problem is given to us in the unit of meters, we'll say the height is also measured in meters. We're also given in the problem that we know this angle of elevation is changing at a rate of 0.14 radians per minute. So this unit of minute here tells us that our time unit is going to be minutes in this problem. Then finally, we want to know what the rate of change of the height of the balloon is. How fast is the balloon ascending? What's dh dt? So looking at the layout of our variables, it looks like we need to find an equation that relates the angle of elevation to the height, because we have those two variables and we have their derivatives. I look over at my picture and I see, there's a right triangle right here. So I can use right triangle trigonometry. Indeed, the tangent of my angle of elevation is the ratio of the lengths of the opposite side and the adjacent side. So this gives me a nice formula that relates h and theta. Indeed, h equals 150 tangent theta. Differentiating both sides using implicit differentiation gives me dh dt on the left equals 150 secant squared theta d theta dt. Again, I'm using implicit differentiation to do this. I have got an equation. Here it has the derivative of h, which is what I want, right? I want to figure out what that value is. I've got the derivative of theta. I know what value that is. Now look at what remains. I've got a secant squared of theta. What theta do I use for that? Well, looking back at the problem, you see that at the instant we're interested in, the angle of elevation is pi/4. So all this is happening when theta is pi/4. So let's plug all that stuff in. I get dh dt equals 150 secant squared of pi over 4 times dH dt, which is 0.14. Secant squared is 1 over cosine squared. So I can rewrite it this way. And the cosine of pi over 4 is the square root of 2 over 2. Squaring that, I get 2 over 4, which is a half. So I end up with 300 times 0.14. And if you multiply that out, you should get 42. And in our case, this is meters per minute. So our final answer is the balloon is ascending at a rate of 42 meters per minute. And there we have the answer. Now you try. Here's a problem that's very similar. I want you to apply the same techniques and processes I did for the previous example to see if you can come up with an answer for this problem. Pause the video now, do that work. When you come up with the final answer, play the video again. You'll see the answer that I came up with. And we'll see if they're the same. I calculated that the rate of change of the angle of elevation with respect to time is 1 over 20 or 0.05 radians per minute. Now that you've done that, I want you to ask yourself this question. Can you tell if the angle of elevation is changing at a constant rate as the balloon rises? Can you tell from what you calculated or from the calculations you've done, is that angle of elevation changing at a constant rate? Use the mathematics to explain what's happening, and then ask yourself, does that agree with your experience as a person?